In our last lesson, we learned about acids and bases and acid-base theory. So now what we're going to do is take our knowledge of the Bronsted-Lowry theory and apply it to weak acid and weak base problems and solve them like we've been doing with other equilibrium problems. So what do we need to know? Any weak acid or any weak base only partially ionizes in water. So that means there are still some acid molecules, some hydronium ions, and whatever the anion is floating around. And because of that, it's going to set up an equilibrium. And because it sets up its equilibrium, guess what? It gets its own K value. So for any weak acid, we're going to set up an equilibrium expression, but we call it Ka. The equation up here is a generic equation that shows how an acid dissociates in water. If we look at the states, everything's aqueous except for the water. Water is a pure liquid, so it's going to be excluded from your equilibrium expression, just like we did in many other cases. The rest of the expression works the same way as before. Anything that's on the right-hand side of the equilibrium arrow goes in the numerator. So that's your hydronium ions and your anion. And then on the bottom is going to be your acid molecule, whichever acid that is. And that's what your equilibrium expression looks like for a weak acid. If you want to see some values for Ka, or if you ever need to look them up for a question, in the appendix in the back of your book, have a look on page 747. Even if you have a few minutes now, pull out your textbook and take a quick look. You'll see that there's quite a range for different Ka values, and you'll find some interesting information there. You can probably guess if we have an equilibrium expression for a weak acid, there's also going to be one for a weak base. So let's take a look at that one now. So if we wanted to write an equilibrium expression for a weak base, we're going to see another K in there, but guess what? Instead of Ka, this one's called Kb. And we use a lowercase b for it. Again, the equation up here is showing an equilibrium that establishes for a weak base in general, B being whatever the base molecule is. Here it's interacting with water. Why do you get B with H+? Well, we know bases are hydrogen ion acceptors or proton acceptors. So that's why we see it gain the hydrogen. And then for it to be a base, it has to produce the hydroxide ion, which we see there. Same thing, because water's involved here in the equilibrium, but it's a pure substance, we leave it out. We can't do anything with its concentration. So on the top, we've got our positive ion, we've got the hydroxide ion, and then on the bottom, whatever that molecule of base is goes there. If you're interested in seeing values for some Kb, they are also in the appendix, page 746. There are quite a few there involving amino-based bases. So they have an amine group, something with nitrogen in their formula. So you can take a look at that as well for some ideas, or even just to read through to see what are some other weak bases, because those are newer things for you, and just even taking a quick glance through the list will help you see some of the different possibilities. Now, we mentioned before in the last lesson, if you have a weak acid or a weak base, it means they don't dissociate completely in solution, generally less than 50%, but often quite a bit more. In some of the problems that you're going to encounter, you'll have to either calculate percent dissociation, or sometimes they even give you that information to help you solve for a different value like pH or concentration at equilibrium. So how do you actually calculate percent dissociation, or if you see that value, what does it mean? The value on the top here, you're going to take the concentration of the acid or the base that's dissociated. Essentially what this is going to mean, if you were to set up an ice table, is going to be whatever your X value is. And we'll go over how to do that with some problems in a minute. But if you recall that X value in ice tables, that's how much dissociates, or that's how much actually is formed when the equilibrium is established. On the bottom, you're going to take the concentration of acid or base that you start off with before equilibrium. Initially means before the equilibrium is established. And that should be given to you in the question. And then if it's a percentage, you know we always multiply by 100. So these are three expressions you should be familiar with, and we'll see them pop up in the next couple of problems. So let's take a look at some calculations involving weak acids or bases and Ka or Kb values. So first problem, we're going to deal with an acid. Propanoic acid's a weak monoprotic acid. A student prepared a 0.1 mole per liter solution and found that the pH was 2.96, and we want to find the Ka and the percent dissociation. So let's take a look first at the question. There's a word in here that may not be familiar quite yet, but hopefully after today you'll remember. It says monoprotic acid. So it's telling us it's an acid, but monoprotic, what does that mean? We know the prefix mono means one, and protic is referring to a proton. And we know when we're dealing with acids and bases, proton means hydrogen ion. So this is important here to know. This acid only has one hydrogen ion that it can lose. And for propanoic acid, this is the hydrogen that it loses. When we get to organic chemistry later on, we'll go over structures of these acids, but that's the acid, acidic hydrogen, sorry, for that particular acid. Okay, next we've got a concentration. This is going to be our initial amount. And we're told the pH is 2.96, so we'll come back to that in a minute. And we want to find Ka and percent dissociation. So if we need to find these things here, this means we need information at equilibrium. So we need to solve some data at equilibrium for this. So first thing we're going to do is set up an ice table. So we need to start with our acid. And we're going to show how it ionizes in solution. So it's going to interact with water. It sets up the equilibrium. Acids are hydrogen ion donors. They give them away. So we've got the rest of our acid molecule, but just take off that hydrogen and replace it with a negative charge. And then where does the hydrogen go? Well, this hydrogen we know is going to go, and the water molecule will accept it, and it makes hydronium. Okay, now we're going to set up the ice table. So let's move this down a little bit and start going with that. Our initial concentration we said was 0.1 moles per liter. This is 1 mole, so we know it's going to lose. And at equilibrium, we've got 0.1 minus X. Next, with the water, pure substance, either leave it blank. I like to cross it out, just so that we know we're not going to include it with anything. We're dissolving in water, so we're going to assume there's no extra ions there. And these have to gain because we're going to increase their concentration. 1 mole, 1x. So at equilibrium, that's just x. And then same thing here, it's going to increase by x. We don't know what x is yet. Okay, so remember the question said we want to find the Ka value. So for the Ka value, that means we need to set up an equilibrium expression. So our negative ion here, our hydronium ion here, and our acid molecule. Oops. One more hydrogen in there. There we go. But we don't have these concentrations yet at equilibrium. We only have X's. So there's something that we're missing in the question. So let's go back up here. I just realized this should be a 2 and not a 3. So let's make sure we fix that. Okay, so there's one other piece of information in the question that we didn't deal with yet. This one here is the pH. The pH actually tells us some very helpful information. So when the pH is measured, it means this solution of acid has been made up, the solution's reached equilibrium, and then you stick in a pH probe and measure what its value is. So this value here has been measured at equilibrium. So this piece of information here is going to help us fill in the equilibrium concentration part in our ice table. And this is where some of your acid-base formulas will come into play and be very helpful. So we can't directly use pH here, but we know we can find out what the concentration of hydronium ions is using our formula where we take 10 to the negative pH. And that's going to give us our X value. So before we can actually go and calculate Ka, we've got to do that extra step there. So for some practice, why don't you see if you can find the concentration of hydronium ions, and when you're ready to check, unpause your video, and then we'll keep going. Okay, so our X value here is going to be equal to our hydronium ion concentration, and we said that's 10 to the negative 2.96. So we're going to punch that in our calculator, and you should get 0.0011 moles per liter. So that's our X. That's going to be our value here. That's going to be our value here. And over here, we can plug that in. And that's going to give us 0.0989 moles per liter at equilibrium. So now we have all of our concentrations at equilibrium, and we can plug them into our Ka. So this number here, we're going to put down on the bottom. That's our equilibrium concentration of our acid. And our X values for our two ions, we have those values that we can stick right in there. So again, let's pause the video. Why don't you try and plug in those values and solve for Ka and check, and then we'll deal with the last part of the question, which was calculating percent dissociation. So let's get back and see if we can solve the rest of this problem. So we're going to put in our concentrations. So that's our X value on the top. We've got our acid concentration on the bottom. And when you plug that in your calculator, you should get about 1.22 times 10 to the negative 5. Or with significant digits, we want two significant digits here. 1.2 times 10 to the negative 5. Now, comes the very last part of the question. We've got Ka. The question asked us for percent dissociation. So, to find percent dissociation, what do? We take the amount that's actually dissociated in the equilibrium, or X value, and we know our X value is 0.0011 moles per liter. Our starting concentration of acid, that was given to us in the question, that was 0.1 moles per liter, and then we multiply by 100%. When we do that, we get about 1.1% dissociation. So it means not a lot of ions form in solution. most of the acid stays as acid molecules, and that small proportion forms ions. Now we're going to tackle a problem involving weak bases. But this one, I'm going to let you try and solve a little bit along the way to see if you're getting the right idea. So let's just walk through the question together, and then I'll let you try and solve some of the answer. The Ka and Kb problems are very similar. There's just usually a few different types of twists with them. But overall, in general, the problem-solving process is similar, but practicing them is the key thing here. So this says the characteristic taste of tonic water is due to the addition of quinine. Quinine has a complicated formula, so we're just simplifying it with the letter Q. Anyone's had tonic water? It's very bitter, and we know bases are bitter, so that's where the taste comes from. Here they're giving us the Kb value is 3.3 times 10 to the negative 6. And here we're asking for a couple of different things. Calculate the concentration of hydroxide ions and calculate the pH if your starting concentration of quinine is 0.0017 moles per liter. Okay, so here's a little different than the previous problem. You have the Kb value, and this Kb value, just as a reminder, it's a very small number. So if you remember, what do we do when we have small K values? We can use a little trick to help us solve. We'll come back to that in a minute. You want to find the equilibrium concentration of hydroxide ions, which means this guy here, we need to find that concentration at equilibrium. And then we want to find the pH. You have to first find your ion concentration of hydroxide before you can get to pH. Once you have hydroxide, then we can deal with the pH at the very end. And they give us the starting concentration of quinine, 0.0017 moles per liter. So what I want you to do now, try and fill in the ice table to the best of your ability, and then unpause and check. And then we'll do a couple of check-ins along the way. I'll let you know when to pause and try out the work, and we'll see how you do. So pause now and see if you can set up the ice table, and taking into account what do you do when you have a small K value. Okay, let's take a look at that ice table. So when we take a look at the ice table, we have our starting concentration of base. It's going to lose by 1x for 1 mole. So we get 0.0017 minus x at equilibrium. Over here, we've got our two ions that form in solution. They're going to gain each by 1x because they're both 1 mole. So we have x and x. Then we see this thing over here in red. Do you remember what that is? This is approximation method. It definitely applies here. Approximation method can be applied to any type of equilibrium problem. So if you see a small Ka or Kb, check it out before you actually try. So when we do our little assumption check, 0.0017 divided by 3.3 times 10 to the negative 6 is definitely greater than 100. So what that means over here, because we're subtracting x, we can just get rid of it completely and go with 0.0017 as our approximate concentration. So now what you have are your equilibrium expressions. We've got a concentration for our base, and we've got our x's for our two ions. Remember, here we're trying to find the concentration of hydroxide. You're given a Kb value here. So what I want you to try next, if you haven't already, see if you can set up a Kb expression for quinine and plug in your equilibrium concentrations to solve for x. When you're ready to check, unpause, and then we'll keep moving on with the pH part of the problem. All right, let's take a look at your Kb. So first, your Kb expression should look like this. Your two ions on the top, your base molecule on the bottom. I put a B in there, but technically I guess it should be Q. So let's fix that one up, even though we're using generic here. Okay. So once we've got that, now we can put in our equilibrium concentrations and our Kb values. So X, X, and 0.0017, those were our equilibrium concentrations, which we highlighted above in yellow. Those are those numbers there. The Kb value, that was given to us in the question. And now the rest of the math is just going through and solving for the Kb. So when we do that, you should get an X value of 7.5 times 10 to the negative 5 moles per liter with significant digits. And remember, that's representing our hydroxide ion concentration. So this here is tackling one piece of the puzzle. One part of the question asked us for the concentration of hydroxide ions. So we got that done. The last part of the question is finding pH. You can't find the pH until you get a concentration to work with. So here we have hydroxide ion concentration. If we want to find pH, remember the formula for pH is log of hydronium ions. So we need hydronium ion concentration. Do we have hydronium ion concentration? No. We have hydroxide ion concentration. So we need a formula that's going to relate something with hydroxide and something with hydronium. There are two options you could use. One would be our pH plus POH is equal to 14 formula, and we can definitely find the POH because we have hydroxide. Or we could take a different approach and use our KW expression, solve for hydronium, and then plug it in pH. Either one will get you to that answer. So given that information, why don't you see if you can calculate the pH using one or those two formulas? In the end, you'll end up with the same pH value. So let's see how you did. I decided I'm going to calculate the POH and then use my pH plus POH formula. So POH is negative log of hydroxide ion concentration. To be more accurate, I'm putting in my unrounded concentration of hydroxide ions. When I put that in my calculator, I get 4.125. But with pH and POH, we always round to 2 decimal places. Remember, 2 decimals for pH and POH. So my POH is 4.13. I need my pH. So that's where my pH plus POH formula is going to come in. So I'm going to take 14 minus my POH, and that's going to give me an answer of 9.87. At the very end, when you're done calculating your pH, make sure that it makes sense. This problem was involving a base, so you should have a basic pH. Remember, bases are going to be greater than 7 on the pH scale. This number is definitely greater than 7, so it falls within the basic range. So there's going to be lots of different variations on acid-base problems and equilibrium. The trick is just to practice a few of each, and the more practice you get, you'll notice that a lot of the problem when you get to the problem-solving process involves a K expression and an ice table. Usually the twists involving weak acids and weak bases have to do something with finding a pH or percent dissociation thrown in there as well. Very last thing for the lesson is what happens when you have other types of acids. These ones are called polyprotic acids. Remember in the first example we just did with the weak acid, it mentioned we had a monoprotic acid. Now what happens if you have polyprotic acid? The word protic, still referring to hydrogen ions, but if you've seen that prefix poly, like polynomial in math, it means many. So with acids here, a polyprotic acid is an acid that produces 2 or more hydrogen ions when it ionizes. There's lots of different polyprotic acids. Here are a couple. Hydrosulfuric acid, it has 2 hydrogen ions. This one can be also called a diprotic acid. This one's arsenic acid. If you look at its formula, it has 3 hydrogens. If you wanted to be more specific, this one's called a triprotic acid. Now, what makes these a little bit different from the other acids is that since there are multiple protons and these are weak acids, each of these protons has its own separate step for ionizing. And each step, guess what, gets its own Ka value. So in a diprotic acid, there's 2 ionization steps and 2 K values. For arsenic acid, there's 3 ionization steps and 3 Ka values. The nice thing here, all polyprotic acids are going to be weak with one exception. Anyone remember this name? This is sulfuric acid. This is one of those 6 strong acids that you should know about. So if you run into a polyprotic acid that's not sulfuric acid, it's definitely weak. So what happens if you actually see one with the equations? Let's take a look at an example with phosphoric acid. Now, at this level of chemistry, we generally don't do a lot of calculating with polyprotic acids, but understanding how they ionize is something that you could definitely see. So, the first equation here, we start off with the acid molecule. For simplicity, I'm going to leave out the states here. It's going to interact with water, and we're going to pull off 1 hydrogen at a time. So we go from H3PO4 to H2PO4, but it's an ion, negative, the dihydrogen phosphate ion, and we get hydronium. That hydrogen that's lost goes to the water. The Ka value associated with this first ionization is 7.2 times 10 to the negative 3. Then, what happens in the second step? This dihydrogen phosphate ion starts it all off. It's amphoteric. It can lose or accept hydrogen. So, here it's going to lose another one with water. 2 hydrogens on the left. It's going to lose one. Guess what? It's HPO4, and now it's got a negative 2 charge. And it's going to make another hydronium ion. Then we do this one more time. We start with the hydrogen phosphate ion. And since it has another hydrogen, it's going to lose one more. So, throw in the water. You get the phosphate ion. And yet another hydronium ion. So here, phosphoric acid is a triprotic acid, which means 3 hydrogen ions. Where are the 3 hydrogen ions in our equation when we look at it from Bronsted-Lowry point of view? Here's 1, here's 2, and here's 3. Now, one more thing worth mentioning before we finish. What's going on with these K values? This is a weak acid, so right away you can see all of the K values are small. But why do they get progressively smaller? This is the initial K value, 10 to the negative 3, small but not ridiculously small. you can imagine when it comes to making some of this first ion, there's not going to be a lot made. Then it's going to further ionize. So you're starting off down here with an even smaller amount than the acid to begin with, and even less of it gets formed to make the hydrogen phosphate ion. The number gets smaller. So of course the K value is going to be tiny because this number is even smaller. And then this even smaller number is going to further ionize, and there's probably not going to be very much of that phosphate ion there. So when it comes to that last K value, it's going to have the smallest value. 10 to the negative 13 is quite a bit different than 10 to the negative 3. So hopefully that helps understand a little bit more about how to solve problems involving weak acids or weak bases, and introduces you to some polyprotic acids.